So this is the chapter 3 material. The PowerPoint will give you all of the concepts. Okay, so don't just watch what I do on the videos and think that you're going to do great on the quiz or on the test. Because the test, at least, is like half concepts, half problems. It's not like the first test where it was just numbers and calculations and conversions and stuff like that. There's a lot more information. I mean, we're talking about Newton's 3 laws of motion. We're talking about inertia. You need to know all those definitions and be able to answer those concept questions. So the chapter 3 homework quiz, it's been up all week. It's due on Sunday by midnight. Don't forget about the discussions. There's still some people who just aren't doing them. So they are worth points. They're due every Sunday. Make sure you get those in because it's 10% of your grade. So that's quite a big portion if you think about it. If you don't do any of them, you're at a B. And that's if you get 100% on everything else. So, all right, let me switch this out. And then we'll start working on some problems. So chapter 3 is all about Newton, all about forces. So that's what our calculations are going to be. So I'm not really going to talk about the concepts since you have all those explanations in the PowerPoint video. I'm just going to go straight to the problems, how we're going to use the equations to solve. So these are physics types equations. We're still going to approach them in the same way that we did before in chapter 2. So the first problem is a tug-of-war scenario. So the reason that I'm looking at this problem is mainly for help in lab. So your lab this semester on force vectors is going to be all about linear force, and it's going to be a simulation. So you're actually going to click, go to a website, you're going to see a simulation, and it's going to be a rope. And you're going to be taking and adding people to different sides of the rope and calculating the net force. So I wanted to do a problem like this to kind of help you understand the lab portion better. So the tug-of-war scenario, we have 2 people, 125 newtons, force to the right. Okay, and then we have 1 person on the other side with 110 newton force to the left. So I said it was tug-of-war. So imagine the rope, the little center there. Over here, you have 1 person, and I'm not an artist, so I do stick people. On the other side, you have 2 people pulling. So we're going to try to figure out who's going to win. And in order to figure out who's going to win, we're using their forces. Who's applying more force? Okay, so we have 2 people pulling with 125 newtons to the right. Okay, so notice I drew an arrow. This is a vector. Force is a vector. So when we talked about scalars and vectors, we said vectors had magnitude, so a number, and a direction. In this case, the direction is to the right. Okay, so I can draw it as a vector. Now, the 1 person on the other side of the rope is pulling with a force of 110 newtons to the left. So we need to figure out who's going to win. So there is an equation given. This is the equation I'll be using in the lab, and it's a net force. So I talked a little bit about net force in the PowerPoints. Now, we're not taking friction into account, okay? We're just doing linear force. We're literally just taking these 2 numbers and essentially adding them. But the trick with this tug-of-war scenario is, since they're vectors, you need to see what direction they're going in. So if they're going in opposite directions, you're actually subtracting those 2 vectors to see the net force. So opposite directions, you're going to subtract. So you're going to take 125 minus 110. So if they were going in the same direction, you would add those vectors. Because if you think of vectors, usually when we add them, we always add the arrows like head to tail. Okay, so if we have 125 newton, it would be this large, and then we have the 110. So we're trying to see the difference between the 2. Okay, this amount here. This vector is a little longer than this one. We want to know the difference. Difference being subtraction. When you think of math, they use the word difference. They're talking about subtracting. So opposite directions, we subtract, and we get a net or a sum force of 15. Now the units are going to be newtons because force is measured in newtons. And so this is our net force, but how do we know who won? Well, you can use common sense almost for that. Who's applying more force, the two people or the one? The two people. So it's going to be these people, so it's a 15 Newton force. They're pointing to the right. So it's these two people that won with a 15 Newton force to the right. So that's how much they won by, I should say. So keep this example in mind for lab. You're not going to see a lot of this on the quiz or the exams. We're going to focus on the more complicated equations, like force is equal to mass times acceleration, centripetal force, gravitational force, weight force, all those guys that we're about to look at now. All right. So since you have the questions in front of you, and for the people online, if you're watching the video, the questions are in the PowerPoint, so you can find them there. I'm just going to write the pertinent pieces of information from the questions instead of spending time trying to write out these huge word problems. So the next one is a 3.9 kilogram, what was that, a boulder? Because I don't have a copy of the sheet, so I just wrote down the important information. So it's a boulder, right?
Yeah.
Rolling down, okay. And it's accelerating, they said, at 1.7 meters per second squared. Should actually be writing this in this form. So we have 3.9 kilograms, 1.7 meters per second squared. And then the question asks us to calculate the force. So we have this boulder rolling down, accelerating, and the force is what they want to know. So essentially what I'm doing here is I'm pulling out my knowns and unknowns out of the word problem. So I know the numbers are important, but I need to attach a variable to them. What are they? Because that's going to help me when I put it in the equation. So if I see kilograms, they didn't tell me specifically what that is, so I would have to figure it out based off the units. So kilograms would be a mass, M. So whenever you see kilograms, grams, pounds, anything like that, it's a mass. Now kilograms are the units we want mass to be in. So we don't have to convert, it's already in the correct units. The next piece of information, they say it's accelerating. So they specifically tell you this is an acceleration. If they didn't, you would look at the units, meters per second squared. That's the units on acceleration. So now we need to calculate force. So this is where you can go to your equation sheet and see what equations you have. Okay, and this is going to be the very first of the force equations, where we simply take mass times acceleration. So this is going to be the easiest type to solve for. You don't have to rearrange, you literally just plug in the numbers and go. So 3.9 times 1.7, don't forget about sig figs. So we have two significant figures in both of these numbers, we're multiplying, so that means we want 2 in our answer. Can you calculate that for me? 3.9 times 1.7, can't do that in my head.
6.6.
6.6. What are the units on force? Newtons, correct. Always newtons. It doesn't matter what force equation you're using, it's going to be newtons in this course. All the time. All right.
Good.
Question? Sorry, what?
Good.
Oh, okay. All right. So now, I said this is the easiest one. Let's look at a harder one. So the next problem is talking about an 825 Newton force. And they're trying to push a car that's parked. So they have a parked car and they're applying a force to it to get that car to move. They tell us that the car is 1,550 kilograms. What else do they tell us? That they pull it for 22 seconds. Right? And then what are they asking us to solve for? Acceleration is one of them. Velocity and distance. So a whole bunch of different things. So these are our knowns and unknowns from the problem. So now, that's our first step. Make sure we have variables for all of them. So newtons, that's our force. Kilograms, that tells me mass. And then seconds is going to be a time for t. So I have all my variables listed so that when I go and look at my equations, it's easier for me to pick out the one I need. So let's look at the equations. So we have force. So the force equation that we just looked at would be F is equal to ma. Is this going to help us solve for any of our unknowns? Because notice we have 3 unknowns, so we're going to need 3 different equations to solve for them.
You get acceleration.
We can figure out acceleration using this. We have force, and we have mass. So we can rearrange to solve for A. Remember, when we're rearranging an equation, we do the opposite operation. So what that means is, if I want A by itself, I need to get rid of M. So since I'm multiplying M times A, I want to do the opposite. So I'm going to divide. So if I divide by M, now M's going to cancel out. Whatever I do to one side of the equation, I have to do to the other. So what this is going to give me is A by itself, but that's going to equal to force divided by mass. Showing that acceleration and mass are inversely proportional, which I talked about in power. All right, random aside. So let's plug in. We have force, 1825. Mass, 1550. And it's looking like I'm going to need 1, 2, 3 sig figs, because that bottom number only has 3. I get 1.18. What are the units on acceleration? Meters per second squared. So it's slightly different than velocity because we're squaring that seconds. Velocity would just be meters per second. So we've solved for 1. But now to solve for the rest, notice the equations that we have on chapter 3 equation sheet aren't going to help us. To figure these out, we're looking back at chapter 2. So our next exam is on chapter 2, 3, and 4. That's because they are all intertwined with each other. Okay? So you are going to see some problems kind of merging between the chapters. So how do we know what equations to look at in chapter 2? Well, it gives us a clue in the word problem itself. It says, this car was at a stop. It was parked before they pushed it. Okay, so if it was at a stop, we're going to look at our 0 initial velocity equations. So, looking in that column, I would look for any equations that had velocity in it. So can I use the most simple one, which is v is equal to at? That's the only one that I wouldn't have to rearrange to solve for velocity. Let's see. I just solved for acceleration, so I have a, and they gave me t. So yes, I can use it. So the hardest part is really just recognizing, oh, I have to look back at chapter 2 equations. The car was parked. This is where I'm looking for them. Once you get the equation, I mean, you're just plugging in numbers and putting those in your calculator. So we have our acceleration of 1.18. We have our time of 22. And it looks like only 2 sig figs for this one. And the units are going to be meters per second. That's actually kind of booking it for towing a car. 26 is what I get. Tell me if you get anything different. So I do enter things incorrectly into my calculator from time to time up here. So this car is being pulled or pushed or towed, or they don't tell us exactly what they're doing to the car, they just tell us they're moving it. A velocity of 26 meters per second. So now let's look at the distance. How far did they pull it? They're going 26 meters per second. They pulled it for 22 seconds, so how far is that? So we're still looking at our 0 initial velocity equations. And we have 2 for distance One of them is that V average one, the V average T. And then the other one is 1/2 AT squared. So these would be the only two with distance, so you would just look at those and think, okay, what one can I solve for? And in this case, we don't have the average. I mean, we could solve for it if we wanted to, but that would require another equation. But we do have acceleration in time, so that's why would you pick the second one? Just to save myself a step. So 1/2 times 1.18 times t, which is 22 squared. And we're looking at, so this one we got 3 sig figs, that has 2, so our answer should just have 2. Which is going to be some weird rounding, I have a feeling. So I have 285.56. So this is one of those weird rounding ones. So I said I just want 2 sig figs. So you start counting left to right. Going to look at the number next to it. Does that stay at 8 or round up? Round up. But we can't just put 29 because this is 200. So we need to stay in the 200s. So instead of that 5, we're going to put a 0 because a 0 isn't a significant figure unless I have a decimal there. So 290, and then the units on it, distance, would be meters. So they pulled that vehicle 290 meters in that 22 seconds. Right. Questions on this one? So this would be 3 separate problems on a quiz or on a test. I wouldn't require you to do all of this for just one. I like to do compound problems in class on the board so that we can solve for several things with just one problem. All right. So moving on then to number 4, we have a Challenger. So a Challenger being a type of vehicle. They tell us that the Challenger is 1944 kilograms. They say this car goes from 0 to 60 miles per hour in 2.3 seconds. Okay, so 0 to 60. So 60. Oops. And 2.3 seconds. So here's the information they gave me, the numbers. So now assign variables. Kilograms is mass. Miles per hour, is that acceleration or velocity?
Velocity.
It's velocity. We just are going to have to convert it. So whenever you have miles per hour, notice when we calculate velocity with these equations, it's in meters per second. So if we use a velocity in those equations, it also needs to be in meters per second. So we will have to convert. Last piece of information is just time. So what is it asking us to solve for? I almost forgot that part. I believe it's at force. Is that correct?
Yeah.
Okay. So the force equation we have so far is mass times acceleration. I have mass, but I do not have acceleration. So that's the only equation I have to solve for linear force. So I have to have acceleration to solve for force. So what that means is I have another unknown that I'm going to have to solve for in order to get force. So, once again, we're going to have to use equations from chapter 2 because that's the equations that had the velocity, times, accelerations, distance in them. How do I know which type? Well, it said that this vehicle went from 0, stopped, to 60. So to go from 0 to 60, that means it was a 0 initial velocity equation. So that's the column we're going to look in. When I look in that column, the most simplest equation where A is equal to velocity over time. So, do I have velocity in time? Yes, I do, so I can use that one. Before I use it though, this isn't in the correct units, so I need to do a conversion. I'm going to do that off to the side over here so that I have the correct units when I put it in the equation. So I'm going to take 60 miles per hour and convert it to meters per second. To do that, so we did this several times in chapter 2, we need that conversion factor, which is 1 mph is equal to 0.447 meters per second. Right, so we always start with what we're trying to convert. So the 60 miles per hour. What goes here is that conversion factor. And I'm going to want to put my 1 mile per hour on the bottom so that they're on opposite sides of the horizontal line, canceling out. That's going to put my 0.447 on the top. This is in meters per second, so my units, once I do this, will be meters per second. 6.82. So we're multiplying 60 times 0.447, and we're getting 26.82. So why am I keeping 4 sig figs when this only has 3? Because this isn't my final answer. Okay? I only worry about sig figs when I'm reporting my final answer. This is a middle conversion. I want to keep as many sig figs as I can to get a more accurate final answer. So that's why I didn't round it. All right. Now that I have the correct units, I can plug it in. So I'm going to put the velocity on top. The time, what was the time again? 2.3 on bottom. Now, I'm looking at just 2 sig figs because time has just 2. I get 11.6, so I'm going to round that to 12. My units, since the acceleration, meters per second squared. Now, I know a lot of the problems that you're doing, except for lab, you're given multiple choice. So you don't really think about units and sig figs as often, but still pay attention to them because I'll give you 2 choices, one with meters per second squared and one with just meters per second. And you need to pick the correct one for acceleration, which would be the top one because of the units. So don't forget about them just because it's multiple choice. All right, so I have acceleration. Now I can solve for force. So plugging it up here. My mass was 1944. Acceleration was 12. Just realizing I could have kept sig figs and stuff. That's it. Oops. That was a big number. Took a lot of force to get that car to go that fast. All right, so 2, 3, 3, 2, 8. We said 2 sig figs. So 23, and then we need zeros for all of those numbers because we want to stay in the 23,000 range. Since it's a force, newtons, it's going to be my units. Questions on that one? Tell me if I'm going too fast. Or too slow, go faster. All right, so number 5, we have a body being dragged across the floor. So they tell us that this body is 72 kilograms. And initially, they're applying a 33 Newton force on the body. So that means is they're pulling a body, dragging the body across the floor. They're applying a 33 Newton force in the opposite direction to get that body to move. Well, then they say, we increase the force. Apparently they weren't pulling him fast enough. So they upped their force to 48 newtons. So we we have two forces, it looks like. And they're asking for us to calculate the change in acceleration. Change in acceleration is often denoted by this triangle, this delta sign. So delta A just means change in acceleration. So let's label these. Well, 72 kilograms, that's a mass. Notice I have two forces, 2 newtons, so when I label them as forces, I'm going to do F sub 1 and F sub 2, just to keep a distinction between them. Force 1, force 2. So how do I calculate my change in acceleration? Well, change in acceleration, or change in anything, is always your final minus your initial. What that means is, I need to figure out, when I apply a 33 Newton force, what's my acceleration? How fast am I accelerating at that force? Then, when I increase my force, what's my new acceleration? Because once I know these, to figure out the change in them, I just subtract them from each other. All right, so what equation am I using? Well, the only force equation we've used so far, F equals ma. I'm just going to be using it twice to solve for each acceleration. And remember, we've already rearranged this equation to solve for A. When we rearrange it, we take force and divide it by mass. So I'm going to start with my A1. So for A1, I'm using the force of 33. The mass of the body was 72. And then I'm going to do the same exact thing for A2 and solve. So my second acceleration, once I upped the force, was 48 for the force. And the body's still the same, right? Body didn't change. It's still 72. Divided by 72. 0.46. Accelerating 2 quickly. And 48 divided by 72. 167. So notice, as the force goes up, the acceleration goes up. They're proportional to each other. When I increase the force, I thus increased the acceleration. So, change in. We're going to be taking our A2 and subtracting it from A1. Subtracting those two accelerations. So I get 0.67 minus 0.46. I'm doing this in my head, so double check my work. Is that 0.21? Okay. Meters per second squared. 0 here just for clarity. Questions on this one? All right, so those are all the ones that I had time to write down. So I'm going to need your help with the information for the next one. What is number 6 about? Someone read it.
What is the weight of a 12.7 kilogram bicycle on Earth at sea level? How does the weight of the bike change on the moon?
Okay.
So you have mass.
So we're given the mass of a bicycle, 12.7 kilograms, and the question asks what is its weight on Earth at sea level. So the reason it says at sea level is because gravity changes very slightly depending upon your elevation. So at sea level, it's exactly 9.8. So it's just saying use what you know for gravity in that question. And then it'll always be at sea level for these types of problems. Then it asks, okay, well, how does the weight of this bike change if it was on the moon? So in physics, weight is actually a force. Okay? It's not, most people think of weight and mass as being the same thing. They're not. Mass is the amount of material that your body is made up of. Weight, how much you weigh, is due to your mass and the acceleration of gravity on your mass. Okay, so weight is a force, and what that actually is F of W. So this is our F of W equations. So weight force. Now, if you look on your equation sheet, so whenever you see what is the weight, F of W is what you're using. On your equation sheet, you see mg for the equation. So you're taking your mass, and then notice instead of ma, acceleration, there's a g there. Well, g, we've used this before when we did free fall problems. We could replace our a with gravity if gravity was the only rate affecting that object. And so that's what we're doing here. So it looks like it only gave you one piece of information, but you actually know another. So gravity on Earth, we already know what that is. We've used it in chapter 2. It is 9.8 meters per second squared. So you're going to be using that to help you solve. But it's also asking for the moon. So gravity changes when you go to the moon. It's less. How much less? It's actually 1/6 of that on Earth. So when we go to the moon, the gravity is going to change from 9.8 to 1.6. So notice we have two gravities, so we're going to be solving for the weight force 2 times. Once for Earth, once for the moon. So let's look at Earth. So F of W, we're going to take the mass of that bike, that 12.7. We're going to multiply it by gravity on Earth, so 9.8. Now for the moon, same mass, because your mass doesn't change just because you go to the moon. It's still the same bike, it's still made up of the same material. Okay? But the gravity is changing. So that's why the weight is going to be different. So 1.6. And then we solve. 12.7 times 9.8. And force, it's, even though it's weight force, it's still a force, so the units are still newtons.
Do we not do sig figs?
You do, so the tricky thing about this, and I've accepted either, is that these numbers weren't given in the problem, so they're known as, they're kind of like conversion factors. You technically shouldn't factor them in to sig figs. So it should just be the numbers in the problem.
Okay.
But if you were to say 120 instead, or just left it at 20, I would still accept it because I know that that's.
So you just get 100 if you counted in sig figs?
I am counting sig figs. So what I'm saying is the mass, this is what was given in the problem, right?
Mm-hmm.
So it has 3 sig figs. Agreed? Okay. Well, these two numbers just have 2, but these numbers weren't given in the problem, yeah. So their exact numbers are kind of like conversion factors, so we don't look at them for sig figs. But I would be lenient in this case just because I understand you're looking here and going, oh, there's just 2. I use both of those in the equation. So sig figs do get tricky. Forgot that I don't have that. Is there questions on weight force? Because next, what are we looking at? Centripetal. Getting into the harder ones. So looking at number 7. So what does number 7 tell us about centripetal force? Anybody read it to me? I don't have it.
An ATV with a mass of 230 kilograms takes a curve with a radius of 18 meters at a velocity of 31 miles per hour.
It was 230 kilograms? Okay, so they specifically said this ATV had a mass of, so they told you that this amount was a mass, but you could have figured that out with the kilograms. The radius of 18 meters. So this is new. Usually when we see meters, we think, oh, that's a distance, that's d. Okay, well the reason they specifically said radius is because right now, we're talking about this ATV taking a turn, going around a curve. So anytime an object takes a turn or goes around a curve, they are doing centripetal forces needed in order for an object to go around a curve, to go in a circle. So every time you go on a roundabout, you need centripetal force in order to turn, okay? So when we do that, we're looking at a circle, right? A turn, a curve. So they say the distance is radius, because radius is half of that circle. This is your R. So it's still a length, just like distance is, D, but they call it radius and label it with R because it's centripetal force and it's the centripetal acceleration that we're calculating. What are they asking us to calculate? AC and FC, centripetal force and centripetal acceleration. Those are the unknowns in the problem, saying calculate the centripetal acceleration and the centripetal force. So, before I start, do I need to convert any of my knowns? Are they all in the units I want them in? Sorry, what was that?
Velocity.
Velocity, we have miles per hour, we can't have that. So, first step, off to the side over here, I'm going to take my 31 miles per hour and convert it to meters per second. So we do that the same way we did last time, starting with the 31 miles per hour. Remember that conversion factor, you'll have it memorized by the end of this semester. Is 1 mile per hour is equal to 0.447 meters per second. So to convert, you're multiplying by 0.447. So what is 31 multiplied by 0.447?
13.86. Do you want 3 decimals for most accurate?
Yeah, if it goes up 3, please.
13.857.
57.
So just don't round when you do conversion.
Yeah, don't round when you're just converting a number to using an equation.
Okay.
You just worry about it in
And
your
you're
final
ignoring
answer.
sig figs, right?
Right. And so these aren't going to count towards sig figs. You're looking at just the original numbers. So looking at these original numbers, I'm going to have 2 sig figs in my answer, my final answers. Does that make sense? Okay. So now that I'm converted, let's look at the equations. Knowing its centripetal force and its centripetal acceleration makes it easier because I have a specific section labeled that. So you know, okay, use these equations now. It's kind of like a highlighted portion. So what do I have for my equations? I got this guy, I got this guy, and I got this guy. So we only have one equation to solve for centripetal acceleration, so we have to use that equation. Kind of narrows it down for us a little bit. Do I have velocity and radius? This is squared. That shouldn't have been down there. Sorry. It did it as a subscript instead of a superscript. We have velocity. We just converted it to meters per second, so let's plug that in. Make sure you're squaring it. And then you're going to divide it by the radius of that circle, the radius of that turn, since it's centripetal motion. And the radius is 18. So 2 sig figs, 11, and it's meters per second squared for acceleration. So even though it's centripetal acceleration, that doesn't change our unit. It's still an acceleration. So now I have acceleration, and I'm going to solve for centripetal force. Notice both of these equations will work, right? I mean, I have mass, velocity, and radius. But now that I have acceleration, this one's going to be so much easier. Less work, less numbers to put in your calculator. So I'm going to use this one. I'm going to take the mass of that ATV, 230, and I'm going to multiply it by the acceleration that I just calculated. And we're looking at 2 sig figs once again. It's going to be a large force. You get it?
2,500.
2,500. What is the units on force?
Newton.
Newtons. For Sir Isaac Newton. Did a lot of these working experiments with force. So, a lot of force. Questions? All right. Let's keep going with it. Let's do another centripetal. I believe the next one's still a centripetal problem, correct? So what does the next one tell us? Is it the carousel or something different?
It's the fighter jet.
Oh, the fighter jet. So this is going to be a huge force. It's going to take a lot more force to turn a fighter jet than it does an ATV. So it's going to be much higher than that 2,500. Forget about that one. What was the mass of the fighter jet?
27,000.
27,000 kilograms.
Acceleration is 88.2 meters per second squared. Radius is of the curve is 525 meters. Then it says calculate its velocity. What is the centripetal force required to accomplish?
All right, so we're doing a couple things. We have a fighter jet, very large mass, right? Because they're big. We have acceleration, so if it's going around a curve or turning, I forget which, but either way, it's centripetal acceleration. So I'm going to add a C to that. Okay, so if it doesn't tell us this is the centripetal acceleration, we would figure that out based off the fact it's going around a curve, it's taking a turn, going in a circle. So there's my A sub C. Now the radius is 925, so that's the radius of the circle of the curve that fighter jet's going around. And then it asks for velocity and centripetal force. Okay, so same equations, which I wish I wouldn't have erased them. Squared over R. I think these are the two we're using, so I'll just stick with that. So it doesn't matter which one you solve for first. You have enough information to do either one. Let's start with the hard one just because, get it over with. And I say hard one because notice this top one. We have centripetal acceleration. We have radius, and we're going to solve for the V. So we have to rearrange it to get VL by itself. All right, so radius is in the denominator. So to get rid of it, to bring it up into the numerator, I'm going to have to multiply by R. Whatever I do to one side, I have to do to the other side of the equation. So what this does is it cancels it out over here, and now over here, I have R times AC, and then V squared alone on the other side of the equation. I'm not done because I want V by itself, not squared. So how do you get rid of a squared? Square root. We've done this before with that distance time equation. It had distance time acceleration in it. So square root of both sides is whatever you do to one side, you have to do to the other. That gives me V by itself. And then on the other side, I need to take the square root of R, A, C. Radius times the centripetal acceleration. So, rearranged equation, let's plug in. My radius is 925. My acceleration is 88.2. And what are we looking at? 3 sig figs for this answer?
Yeah.
Units or meters per second? Or my designated calculator person. 286 meters per second. So quite a high velocity, right? Which makes sense. I mean, it's a fighter jet, it's not a car. It should have high velocity. But now, let's calculate the force. We got a C here. Centripetal force. So we saw with an ATV, it took 27,000 newtons. So can't imagine how much this is going to be. We don't have to rearrange, we just plug in. We plug in the mass, and we multiply that by the 88.2, the centripetal acceleration. Notice we're only having 2 sig figs. That's going to be huge on my calculator just so that I know how many zeros. Oh, wait a minute. So 24, we would have to round it up. And then 1, 2, 3, 4, 5 zeros. Those of you at home wondering probably, well, how the heck I got that. This is the number my calculator spit out. Okay, so we said 2 sig figs. So I said 1, 2. Look to the number next to it. That 3 is going to go up to a 4, so that's how I get the 24. But now, for all of these rest of these numbers, I need placeholders so that I'm still at the same order of magnitude. So these will be the zeros. So that's why I have 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros. So 2,400,000 newtons. So a lot of force. Huge. So I want to mention real quick, along with the homework quiz, I have a practice worksheet with some practice problems because I know we're kind of getting into a little bit more difficult problems. So it's got an answer key as well. If you wanted to do those practice problems, check the answer key just for extra practice. That'll help in the come exam time. So, are you guys able to access your quizzes after the fact and see the questions and the answers?
After you take them, it's just,
But can you go back and look at them again to study with for the exam?
I haven't tried.
You haven't tried yet? Okay. I was just wondering, because if you can't, I'll try to figure a way to make you be able to, just so those would help. All right. That was it for centripetal acceleration. So the last equation in this chapter, gravitational force. So we just saw a force of 2 million newtons, huge force. Now, with gravitational force, these are very, very tiny, minute, small forces. What gravitational force is it's the force that you exert on everything around you, and the force that everything around you exerts back on you. Okay, so these are so small you don't even feel them. But they're real so that we can actually calculate them. Okay, so right now I'm exerting a force on the markers on the board, and they're exerting a force back on me. So how do I figure out what that force is? Well, I use the gravitational force equation. And notice, so just to talk about some of the aspects of this equation, there's two masses. You have an M1 and an M2. That's because gravitational forces are between two objects. So like me and the eraser, me and the people in this room. We're all exerting forces on each other right now, and we're going to be able to calculate what those forces are. So it depends on the masses of the objects. So the more the object's mass, the higher the gravitational force that they'll exert on each other. It also depends upon radius or distance. Okay, so we're using r for radius again, but it's really just the distance between the center of masses of both objects that we're comparing. So this r value needs to be in meters, just like distance, just like radius was when we did centripetal force. So notice there's one variable I didn't talk about, that big capital G guy, and that is the gravitational constant. So you need to use the value for the gravitational constant every time you're calculating. Don't leave this out. Do not even ask me how they came up with this gravitational constant, because I don't know. All right. So now let's apply. Can someone read me the first question of the gravitational force problems. PowerPoint.
Calculate the force of gravity between a person with a mass of 90 kilograms and a car with a mass of 2,000 kilograms, whose center of masses are 10 meters apart.
Thank you. So it said calculate the gravitational force between two objects, a person, 90 kilogram mass, and a car, vehicle with 2,000 kilogram mass. So since I have two masses, I label them M1 and M2. Doesn't matter the order. I'm multiplying. I could flip it. person could be M2 and the car could be M1. It's still going to get the same answer. Then it says their center of masses are 10 meters apart. So that 10 meters is not a distance. I mean, it is a length like distance is, but it's going to be our R value. So just pay attention to what variable you need to be putting for that. So now, all you do is plug in. The hardest part about these types of problems is actually the calculator work, because you're using scientific notation in here. So make sure to include for G that gravitational constant of 6.67 times 10 to the negative 11. And then my M1, so the person is 90, the car is 2,000. And then on the bottom, how far apart are those two objects? Well, they're 10 meters, but we need to square that. It's still a force, it's still going to be measured in newtons. So now, if you're at home, I would calculate this in your calculator to make sure that you know how to use your calculator with scientific notation. Hopefully you figured that out already in chapter 1 though.
So do you account for the sig figs only
Sig figs in the numbers given,
yeah, so not the constant?
not the constant. Yeah, because this is like a conversion factor essentially.
So you just want one?
Just one.
Did you get your answer in scientific notation?
I do not get mine in scientific notation, unfortunately.
Is it okay if you get it?
Yes, both answers are correct. I'll write it both ways. How many? 1, 2, 3, 4, 5, 6. 1, 6. So that would be 1 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 7. So the reason there's two answers written on the board depends what your calculator mode is set to. This would be the normal notation version with 6 zeros and then a 1. This would be the scientific notation version. Both are correct. This is why scientific notation is nice, and you don't have to count all the zeros, make sure you have enough. You just need to make sure you have the right exponent. So notice how tiny that force is. We went from a 2 million force with a fighter jet now to this tiny, tiny, minute force. That's why we don't feel it. Okay, so the next one, I believe, is the force between two vehicles, right? They have the same mass. What's their mass?
2,000
2,000? What you said?
kilograms.
Okay. So the next problem, we're calculating F of G again, but now it's between two vehicles. And both vehicles have the same mass. And this is just coincidence. Usually they are different masses. But our masses just went up. So what I expect is, since the masses are much higher, my gravitational force is going to be higher as well. Because gravitational force and the masses are proportional to each other, which means if one goes up, the other's going to go up too. So, what are their radius? How far apart are they?
6.2.
All right. So, instead of rewriting all this, I'm just going to leave my gravitational constant up and plug in my new values. So the vehicles, 2,000 times 2,000. That's their masses on top, and then we're dividing by how far apart they are. So the distance is less than the last problem as well. And by as well, I mean, since the distance is less, they're going to have a higher gravitational force due to that as well. Because gravitational force and distance are inversely proportional. So the closer the objects are, the higher the force, the farther away, the less. And that's one of those concept questions that you'll need to know for the exams and the quizzes. So, all right, so let's calculate this guy. Too busy talking, let's calculate. There's 11. I get, how many zeros is that? 5 this time? 1, 2, 3, 4, 5. Is it just one sig fig? Yes. Or 7 times 10 to the
-6.
literally go and count. So both these answers are correct. One's sig fig, one's in scientific, one is not. They're both in Newtons. And notice, this number is larger than our last problem. Our last answer was 1 times 10 to the negative 7. Okay, it had an extra digit, so it was 1 decimal place further out. So since their masses were bigger, since the objects were closer, their gravitational force was higher. Questions on this topic at all? I haven't looked at the time. I didn't go over time today. No, I didn't. Good.
So if you did like the Earth and the Moon, you'd get a big number.
Yes, I actually, on the practice worksheet, I have an example with the Earth and a person. So if you calculate that, you're going to get, I mean, it's not going to be huge, but it might be in the hundreds range for the person and Earth. Between the Earth and the Moon, I mean, I would expect it to be rather large because of their masses, but you also have to take into account their distance.
Yeah, that's
Because that's inversely proportional. So the further apart they are, that's going to make the FOG go down. So I don't know, that'd be an interesting one to see. Because in the example of the person in Earth, I did it from the center of Earth, so that was like 5,000 kilometers or something. So that was quite a big distance as well, but nothing compared to the Earth and the Moon.